this video, I'm going to start by doing something I promised I would do in the last couple of videos. I'm going to explain to you why our regression line is called the least squares regression line, why that's so important. I'm going to do it using my Fathom software. I'm also going to show you R squared, the R squared statistic. This is something I think I mentioned last year in pre-calc, but we didn't really get into what it means. The other thing is that R squared, the basics of it is that it is the R value squared. You know, it's calculating, it's easy, it's what you think it would be. But it has a very particular meaning, and we're going to talk about why it's so important and so interesting. So let's start with this. We're going to start with the data that we talked about last video, and a data set that a number of you collected last time, the height versus right foot, right? This data set, this scatter plot hopefully looks familiar to you. But what I've done is I've put a line here, as you can see. And this line is right at about 9.52. It's actually 9.53, that's the closest I could get it. But 9.52 is the average of the right foot length, right? So if X was no predictor of Y, if there was no correlation, if this was useless to us, well then the best thing we would have is just the average of the right feet, right? I mean, that's the best predictor we have if we just had this data. If the heights meant nothing, this is what we would use to predict what the average right foot length is, right? But as we can see, there does appear to be a relationship. So we're going to make a comparison of what it's like if there was no relationship versus if there is one. So what we use to do that is something called the sum of squares. And okay, I'm going to show squares. Here it is. I'm going to show you squares. Look at my lovely squares. As you can see, these squares come from distance between my line and the actual data points. So, in a sense, it's your y values versus the y hat. So, in this line, our y hat is just 9.52, or 9.53 in this case. It's close enough. It really doesn't make a difference. The sum of squares is 10.68. So the area of all these squares, so the distance from 9.52 to each actual y value squared is 10.68. So let's take a look at that for a sec. Now here's the thing, you can see some of these squares are quite big, right? That's a clear indicator that this model does not really predict the data very well, does it? No, of course not, because we can see there's an upward trend, and this line doesn't describe that. So I'm going to try and move this line around a little bit, and you'll see once I do, these squares make a little smaller, don't they? My sum of squares is down to 6.8. Let's see if I can make it better. Let me see if I can line this up even a little better. I'm down to 2.716. See if I can still do better. Let me see, oh, that square is a little big. See if I can do something about that. I'm down to 1.99. I'm less than 2 now. So you see, I was at like 10.68 originally. And now I've gotten to under 2, 1.981. See how my squares are much smaller? That indicates this line is a better and better fit for the data. So what I'm going to do now is I'm going to get rid of this movable little line. And I'm going to put in the least squares regression line. And this line, based on calculations by the computer, is the line that will give us the smallest sum of squares. And there it is, 1.968. Excuse me. So we got pretty close with that movable line, right? I was able to get it down to about 1.9 or so. 1.99 or 1.98. But I was really close. The smallest sum of squares possible is 1.968. And that's from this line right here. It gives me a little equation. And this should look familiar because this is the equation that we did yesterday. It's 0.227x minus 5.125. Oops. No. What did I do? What have I done? Oh. Scared the crap out of myself is what I did. Okay, it's here. We're good. Let's see if we can drag this a little bit so it's not up against the wall here. There we go. Come on. Stop that, you. So it'll be y hat equals, and I'll put the 5 at the end there like I was supposed to. Whew, okay, that was almost a disaster. But it wasn't. We're good. So, again, you can see the regression equation. It gives us the sum of squares, right? Now, this sum of squares is 1.968. 1.968. So, I'll put that here. And that's real nice because originally, my sum of squares, if we just look at the mean, if there was no relationship, it was 10.68. So we were really able to cut down a lot of this fluff, if you will, a lot of this extra room in those squares. Now you also notice with this readout, it gives r squared right here. R squared is 0.82. Let me show you where that comes from. So I went from 10.68 to 1.968, right? That is a difference of, if I can get my calculator real quick. Let's see, 10.68 minus 1.968, that's 8.712. I was able to get my sum of squares to go down from here to here. I was able to make a decrease by 8.712. Now here's the thing, it's 8.712 out of what I originally started with, right? Out of that 10.68. So out of that 10.68, I was able to get rid of 8.712 by way of the least squares regression line. And so as a percentage, 8.712 out of 10.68, that is, as a decimal, 0.8157. Of course, if you round it, it becomes 82. There it is, right here. That's what r squared is, folks. It's basically the percentage of the least squares that is eliminated by having this line. So it's basically the percentage of the variability in the y variable, which is our right foot length, that gets accounted for by this linear relationship. Because as a result of this linear relationship, as a result of this least squares regression line, we're able to account for 82% of the sum of squares. Now, of course, there's still squares, right? There's still some variability. The line's not perfect. So, that 18% is due to other factors. Maybe it's sampling error. Maybe it's just, differences in people. Your height is not a perfect predictor of your right foot length, and I don't think anyone would claim that, but still a very good one. Your height accounts for 82% of your right foot length. And then the other 18% will be accounted for by other factors, according to this data. Now, of course, it's only 12 data points. We need more data to get a better idea of what the truth is. But based on our data set, 82% of your right foot length is a result of your height, is what that's saying, basically. So, let's just look at this for another sec. If you want to pause it. Again, this sum of squares, if you ever go into advanced statistics, which I think a number of you might when you get to college, I hope you do, the sum of squares really comes out big time. It's something that really is an influence and a factor in a lot of different statistics that you'll study. This is all you're really going to see of it here. AP exam doesn't really make you do much with it, but just know that it's important. Just understand that the smaller that the sum of squares is, the better, right? Because that indicates that we're close to the data points. The further away you are from the data point, the bigger the square is. You guys saw that when I had the straight line. We had a real big square down here, we had a big square up here, but now they're all nice and small. And that's what we want. Make it as small as possible. So that's what it is, folks. That's the idea of the least squares regression line. It's the line that makes the squares the smallest. The sum of the squares cannot be smaller than what it is with the least squares regression line.